Greetings and welcome, ladies and gentlemen. You've made it to video number 2. You're still in Math 4. Congratulations for not surrendering and dropping out already. We're going to go the whole way now. There's no backing out. So today we're talking about solving systems using elimination. So this technique can be used to solve the same exact types of problems as the ones we did yesterday, where we had substitution method. Elimination solves the same kind of problem, but it's just a different approach, and it will often deal with your many coefficient problems in a much nicer way. But I think what I want to start off with is a little recall concept. This is what I'm going to do, recall, right here, where I'm just going to ask us to add some fractions. All right, and this might seem extremely arbitrary, but this is actually going to be quite helpful to us. Let's say I've got 2/3 plus, I don't know, 5/7, and I want to add those. What would I do to add those fractions? Because just so you're aware, I'm not allowed to just say this. I don't just like add across. That would be super illegal. Multiplication behaves that way with fractions, but addition and subtraction does not. So what would we do? Yeah, we'd find the LCD, the least common denominator, between 7 and 3. And what is that LCD? 21. And then I'd have to multiply each of these by the part of the LCD that it's missing. So I'd multiply this by 7/7, top and bottom, because 7/7 is the same as 1, right? And multiplying by 1 is legal. It's not going to change the value. And this one I'd multiply by 3/3, right? So I would have 14/21 plus 15/21. And that would equal, looks like, 29/21. And I'm done. Right? So this concept of LCD is actually going to help us tremendously in the idea of multiplying each fraction by the part of the LCD that it's missing. That's the primary skill that we're going to have. Now, sometimes when adding fractions, let me give you like one more little example. What if I had, I don't know, like 5/8 minus, I don't know, 3/12 or something like that. So a separate problem here. Now in this case, the first example, I just want to point out that we actually found the LCD by multiplying each denominator by the other denominator, right? The 7 was multiplied by 3 and the 3 was by 7. But that's not just what those numbers come from. Technically, you could multiply this by 12/12 and this by 8/8, and you'll get a common denominator, but it won't be the least common denominator. And mathematicians are often not just looking for the right answer, they're looking for the fastest and easiest way to get there. I used to tell people, and well, to be honest, I still do, that I'm an efficiently lazy person. I'm interested in minimizing energy and maximizing output, right? Like I want to get the most bang for my buck sort of thing, right? So what is the LCD in this case between 12 and 8? 24. Well, the LCD, I'm looking for a number that both of those divide into evenly. So not a number that goes into both of them, but a number that they both go into, and the smallest one. So it would be 24, I believe. Right, because 8 goes into 24 3 times, and 12 goes into 24 twice. So, oh, I could, technically. Yeah, you're right. Okay, so you did have a cleverer approach. That was a failure on my part in creating a problem that couldn't be done. But yes, you could have reduced this to 1/4, and then your LCD would have been 8. And yeah, that is actually the best way to do it. But for the sake of my example, we'll pretend that can't be done for fun, just now. But yes, good call. Absolutely right. So we'd multiply top and bottom of the 8 by 3/3 and the 12 by 2/2 to get our LCD common denominator thing going here. So we'd have 15 24ths and minus 6 24ths. And now I subtract those all normal, like 15 minus 6 is 9 24ths, and I don't believe that reduces. Wait, right? 9? Yeah, I did that right? Yeah. Now I'm trying to figure out, wait a minute. That does reduce, friends. Oh man, clearly my summer brain is still in effect. Those are both divisible by what? 3. Right? 3 goes into 9 3 times and into 24 8 times. There, 3/8. I was going to say, it has to reduce if you could have reduced this earlier and had 8ths as your denominator. So once again, I just want to point out, you multiply each denominator by the part of the LCD that it is missing. If you've got that skill and that understanding, we can do this elimination method. So let's do our first example of solving by elimination method here. So solve using elim. So let me get you a problem here. How about burger? This one sounds good. Let's say I've got 2x plus 3y equals 7 and negative 4x minus 5y equals 13. All right. So there's a few steps to elimination. I think I think we'll do this problem with steps that I write out on the side, is what I think I'll do. Step 1 for elimination. Actually, let me give myself some room here. Step 1 for solving by elimination is line up like terms in columns. All right. And technically, step 1 is already done here. I just want to point out that my x's are all vertically aligned, my y's are, my equal signs are, and my constants are all lined up. Okay? Now, it doesn't have to be xy equal constant. It could have been y equal x constant, right? As long as they're lined up, that's what we need. Okay? Step 2 is the tricky step. And it's really wordy. Let's see. Multiply each equation by, let's see, I'm trying to think of the right words to say, by a number that will give you opposite coefficients. For one of the variables. Alright, so that's kind of a weird, wordy sort of instruction, but this is the idea. First of all, what do I mean by opposite coefficients? Coefficients are the numbers in front, right, of our variables. So here a coefficient is 2, and here a coefficient of the x is negative 4. So those are not currently opposite. They are opposite in sign, right? One's positive, one's negative, but they are not opposite numbers. Okay? So if those were truly opposite, I would have like 2x and negative 2x. All right? And it doesn't necessarily have to be the x's. I'm specifically targeting one of the pairs of variables, right? I could have had, positive 3y and negative 3y. All right? And that's what I'm looking for. And the way you'll figure out what we multiply each or even one of the equations by in order to get these opposite coefficients is by kind of thinking about LCDs. All right? What's the smallest number that both 2 and 4 go into? Smaller, right? It's 4. Right? And what's the smallest number that both 3 and 5 go into? 15. So in my case, I'm going to try to shoot for opposite x's merely because this is smaller than the opposite y's would be. All right, so this 4 is literally like finding the LCD between 2 and 4. All right, that's where those numbers came from. They're not technically LCDs, and I'm just writing them up there temporarily so I could do that kind of initial analysis. So now what I'm going to do is I'm going to multiply one or both of the equations by some number in order to get opposite coefficients for the x's. So what would I have to multiply this top equation by in order to get a 4x? I'd have to multiply by 2, and the whole thing is being multiplied by 2. What do I have to multiply the bottom equation by in order to get a 4x? Or in this case, a negative 4x. It already has it, right? And better yet, it's already negative because I want them to be opposite, right? I'd want like a 4x and a negative 4x. Okay? You don't necessarily know why I want those opposites just yet, and that's fine. I'll let you know in a moment. But that's the goal, okay? Now, just as a quick question, what would I have multiplied the top equation by if I wanted opposite y's? You'd multiply the top one by 5 and the bottom one by 3, and I would have gotten a positive 15y and a negative 15y. Okay? So you wouldn't have been wrong for doing that, you just would have had larger numbers, is all it is. So let's see, let's multiply this top equation through. And I'm going to write my results kind of right underneath this other one. So 2 times 2x is 4x, 2 times 3y is 6y, and 2 times 7 is 14. Okay, so step 2 is done. I've obtained the opposite coefficients that I wanted in doing so. All right. Step 3 is add the equations together. And solve. All right, so literally kind of like adding like this, just put a bar down and add negative 4x and positive 4x is 0 x's. We have eliminated the x's. All right, that's where the name of this method comes from. I eliminated one of the variables, and now when I add the y's, negative 5y plus 6y is 1y, and 13 and 14 is 27. Now, sometimes you'll have something like, 5y equals 35 or something like that, and then you'll have to finish solving. But what it does is by getting those opposite coefficients, I was able to add those equations together, eliminated one of the variables, and I'll always be left with another equation with only a single variable left, which is something we know how to solve. Okay? So, let's keep going here. Let's see. Now I've only solved for half of the answer. So I'm going to have to figure out what x is equal to. What are your thoughts on how we could find x? Yeah. We can just plug this in. And in fact, it doesn't matter which equation we plug it into. It could have been either. Technically, I could have even, well, I can't, no, I could have actually plugged it into any of these equations as long as the equation has both an x and a y. Back in substitution days, with our revised equation, it was super important that you plugged it into the other equation. This one doesn't matter, okay? So it won't affect us. So I'll probably just pick the original top equation merely because that x looks small. I don't know, the numbers are tiny. I'm a fan of smaller numbers. So 2x plus 3 times 27 equals 7. And now notice I've got a single equation all in terms of one variable. So I can solve this. 2x plus, let's see, 60 plus 21, 81 equals 7. Subtract 81 from both sides. 2x equals, what's that going to be, negative 74, and then divide by 2. And I'll get x equals, what's that, negative 37. Okay, so there's my solutions. Oh, I didn't write the last step. Substitute answer into, and I'll just write any of the previous equations. And solve. Right? So my goal is to end up with 2 solutions. Now if I tried this problem using substitution, notice that I would have had coefficient, 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 and it would have been really ugly, and no matter which variable I tried to solve for, I actually would have ended up with fractions in my work, but I still would have ended up with my whole number answers. All right, so elimination is particularly good in solving problems where you have coefficients other than ones or negative ones in front of all of your variables. And that's kind of its strength. Okay, so that's what we've got going on here. Let me see if I can find us another problem that I can make up. Maybe I'll make this one up. That might be dangerous. Okay, here we go. I'm going to make it up. It's going to be scary. Let's see. Let me come up with some numbers here. Watch this. Here we go. I'm going to have 5x minus 8y equals something. Let's see. 2, how about? And then I'll have 4x plus, let's have 12y equals 20. And this will be our last little example for today. So, step 1. What was step 1 in elimination method? Line up my variables. They happen to be lined up in this case. Okay, that won't always be the case. I mean, I could have had 5x equals 8y plus 2, and I would have been like, oh, I should add 8y to the other side just to take care of that. So that's not always going to be the case, but step 1 is done. Step 2, multiply one or both equations by some number in order to obtain opposite coefficients. So before I even do that, I like to do kind of, some analysis where I can figure out what will my, opposite coefficient, what would that number be? What is my quote-unquote LCD between those numbers? So between 5 and 4, what would the number be that those divide into evenly? 20. And between 8 and 12? 24. So I'm going to choose x's, all right? You still will get the same answer if you chose y's. There's no problem with that, okay? No problem whatsoever. And in this case, I'm going to have to multiply both of these equations by something in order to get opposite x's. The first example, we only had to multiply one thing. So let's see, for the top, what would I multiply 5 by in order to get 20? 4. And the bottom, I'll make this my negative 1 because they need to be opposite. What would I multiply 4 by to get a negative 20? And in this case, I'll make it negative. You could make the top one negative, doesn't matter. All right? Doesn't matter. But do you guys understand that this step is really the primary step to this whole process, is understanding what am I going to multiply these by in order to get my opposites so they line up, okay? But I feel like we're doing this pretty good. I think we got this. So let's see, let's multiply the top equation. And by the way, a super common mistake people have is they forget to multiply, whoa, over there. Yeah, that was scary. They forget to multiply all parts by this thing. They might only just multiply the left-hand side. So just be careful of that. Make sure you multiply everybody. So 4 times 5x is 20x. 4 times negative 8y is negative 30 dos y. And 4 times 2 is 8. Negative 5 times 4 is negative 20x. Negative 5 times 12 is negative 60y. And negative 5 times 20 is negative, what am I blanking for? 100? Wow, geez. Whew. I wanted to say 80 so bad, I don't know why. So, have I obtained my opposite coefficients? Yes. So step 2 is done. Step 3, add them up. Add them up. Here we go. 20x and negative 20x is 0. Negative 32y and negative 60y is negative 92y. And actually, I think I like where this is going. 8 and negative 100 is negative 92. All right. So have I solved for y yet? No. This one takes a little bit more work. Not much. Divide both sides by negative 90 dos. And you'll get y equals 1, because a negative divided by a negative is positive, my friends. And then what we'll do from here is what? How do I solve for x? Yeah, which problem you guys like? I like the 4x one too, sure, why not? Why not? So we'd have 4x plus 12 times 1 equals 20. 4x plus 12 equals 20. Subtract a 12 from both sides. 4x equals 8. And then divide by 2, 4. Divide by 4, and we get 2. That's the one. X equals 2. So we get our solution. All right, but the key to the elimination process or method is multiplying and getting those opposite coefficients. Now, sometimes you'll get both pairs to end up being opposite coefficients all in the same move, and then all of your variables will eliminate, and then that will be the situation where you either end up with an infinitely many solution situation or perhaps a no solution situation, depending on if when the variables disappear, if you get something like 0 equals 20, that's false, no solution. Or if you get something like 10 equals 10, if it's a true statement, then you're like, aha, there are infinitely many solutions, and they happen to be the solutions that lie on either of the equations because they happen to be the same equation. All right, so those represent lines, remember. The reason, by the way, this is called linear combinations is because when I get my opposite equations, I'm combining the equations of two lines to get a third different equation, but it's simplified. So that's the other reason it has that name. But that's the big idea. I think we're good on this. Sounds great. Bye, Internet World.